post-equivalence point, our approach to be able to solve this one is pretty much what we've already done for the pre-equivalence point regions. However, post-equivalence, we take note that we have already an excess of your tin 4. And all of the vanadium has been used up. So post-equivalence, we just use whatever it is that is in excess. That is to say, we base all of our computations on our tin 4. So we try to do the same tack as what we've done in our first video for today. We compute after adding a volume of 50.10 ml of the tin 4. Let's try to compute now just how much tin 4 it is that we've added. So that's 50.10 ml times 0.05 molar of tin 4. So that is a total of 2.505 millimoles of tin 4. To this, we subtract the amount of tin 4 that has reacted. So we get originally 50 ml of the 0.1 molar vanadium. Now all of that has reacted according to our overall redox reaction, wherein 1 millimole of tin 4 reacts for every 2 millimoles of vanadium 2. So plugging it into my calculator, I get 2.5 millimoles of tin 4. Now get the difference. We can now compute the moles of tin 4 that is left post-equivalence. That's 2.505 millimole minus 2.5 millimole equal to 0.005 millimoles. We also need to know just how much of tin 2 is been produced in the overall titration. So since we have reacted 2.5 millimoles of tin 4, we can just apply stoichiometry basing on our overall redox reaction. And as we can see in here, 1 millimole of tin 2 is formed for every 1 millimole of tin 4 that reacts. So that's actually 2.5 millimoles of tin 2 that has formed. So with the amounts of tin 4 and tin 2 already known, what we can do next is we compute the concentrations of each ion. For tin 2, that's 2.5 millimole divided by the overall volume. We started off with 50 at the very beginning plus 50.10. So that's 2.5 over 100.1 That's around 0.025 molar. And doing the same for our tin 4, we get 0.005 millimoles of the tin 4 divided by 50 plus 50.10 ml. So that's 0.005 over 100.1. That's around 5 times 10 to the negative 5 molar. Now to compute our cell potential, we once again use our Nernst equation. That's E equals to E naught minus RT NF ln the tin 2 divided by the tin 4. Oops, sorry for that one. Now from our table, we can see in here that our E naught value for tin 4 is 0.154 volts. So let's use that one. That's 0.154 minus 8.314 T times N. Basing on our table, the N should be equal to 2. We always look at our table of reduction potentials when we use our Nernst equation. Ln, the concentration of the tin 2, that's 0.025 divided by 5 times 10 to the negative 5. So let me just input it all. That's 0.025 divided by 5e negative 5. Oops. Again, I have to apologize for this one. Making videos really makes me feel rather anxious. That should be the other way around. So I deeply apologize for this. So let me just correct myself in here. That should be tin 4 divided by tin 2. Anxiety. Wow. So, plugging all of these values in to our calculator, we get E is actually going to be equal to 0.234 volts. So for all of the other volumes, post-equivalence, we follow basically the same procedure. So you can now try to compute what the cell potential is at 51 ml and also at 60 ml. Again, I'll be posting on Blackboard the values for these so that you can check if you have the correct values.